Good morning, good afternoon, and good evening. Welcome to the fourth edition of this mentoring session. My name is Thomas Basikolo from ITU, and I'm excited to be joined by my colleague Miya, who is going to go through the session. In this session, we're excited to talk about a little bit advanced topics in machine learning, which is model optimization as well as model compression. In the past three sessions, we talked about communications, introduction to communication networks. We did also talk about data preprocessing, machine learning model training, and now we are on the optimization and compression. So we're looking forward to having your participation in this session, and I would like to welcome Miya. Hi, Miya. Good afternoon.
Hello. Thank you for the lovely introduction. Hello everyone, and welcome to the fourth mentoring session for this year's AI and 5G challenge. My name is Miya Nishio from ITU, and I am very happy to see everyone who's joined today. So just as Thomas explained, until this point, our mentoring sessions have mostly concerned the simplest steps of the machine learning process, but today we'll focus on something a little bit more difficult, so on model optimization and compression. So if I just share my screen real quick. Hopefully everyone can see my screen. Okay, so for those who have missed our previous mentoring sessions, we had 3 so far. The most recent one on September 29th was just released on YouTube yesterday, and this week's mentoring session will also be released on the neural network and YouTube soon. You can also find all of our previous resources on the GitHub repository, as mentioned here. If I could ask Thomas to also release the link in the chat as well. You can also find the resources we'll be using today in this GitHub. So if you'd like to download some data and download some code as well, it's all on there. So as usual, we're going to start off with a simple explanation on model optimization and model compression, followed by a hands-on Jupyter notebook session, and then finally a Q&A session at the end. So last week we focused on, or not last week, sorry, the last session we focused on model building and training. This week we're going to be looking at the steps in between model building and training just until deployment. And then again, as usual, this is the recommendation from ITU TY.3172 that shows how the machine learning process works in communication networks. So first, let's take a look at model optimization. So what is model optimization? Optimization is the process where we train the model iteratively so that it results in better accuracy. We can do this optimization process by using something called optimization algorithms. So one of the most popular and well-used algorithms, as I'm sure you've already heard, is gradient descent, which I will explain more about in a second. However, if you're dealing with deep learning, for example, you might want to consider using, for example, stochastic gradient descent with momentum, RMS-prop, and add-on optimizer. So before we get into the explanation of what gradient descent actually is, I'm just going to quickly explain what logistic regression is so that we can see where gradient comes into place. So with logistic regression, we set up a function that takes weights beta, inputs x, and then produces predictions y. In logistic regression especially, we put this y through a sigmoid function to limit it to a value between 0 and 1, which we can then use to classify between 0 and 1. However, we then input the results of the sigmoid function into a cost function to see the difference between the predictions and the true results. And this error is then sent to the optimizer to calculate a new set of weights for the original function so as to minimize the loss. So this is where gradient descent comes into play. So let's say our cost function or loss function today is y equals x squared. And x would be basically the weights that we're inputting. We would first start off from a random point. So this is like setting a random set of weights for our model. And then we input x equals -3. We calculate the gradient. We set a learning rate, which basically decides how fast the calculations are going to go. let's just say for now. And then we put it through this function here, which decides that the next step is the former step minus the learning rate times the gradient. So again, if we started from x equals -3, our first iteration would basically look like this. And then we would repeat it over and over again. And as you can see, it would slowly decrease. And we would do this until the nth iteration, or the nth value that we get here is bigger than the nth take away 1 value, so that we can find the global or local minimum. So as you can imagine, with a large data set, we would have lots of x's to calculate. And so when we're actually doing this calculation, we don't really want to be calculating so many gradients. And so what we would do is we would use something such as stochastic gradient descent, which only takes a subset of the original data. And so we can minimize the amount of calculations that we have to do. So this is gradient descent. We also have something called hyperparameter tuning. So as briefly mentioned last time as well, hyperparameters are classified as two kinds: model hyperparameters and algorithm hyperparameters. Model hyperparameters basically influence the performance of the model, so it increases accuracy, for example, and algorithm hyperparameters affect the speed and quality of the learning process, but don't affect the performance of the model. So these are things such as batch size, epochs, and learning rate. So these are just some examples of some hyperparameters that you might end up having to choose. Obviously, what you choose here kind of depends on the machine learning algorithm you decide to use. So with these, there's obviously lots of different kinds of combinations you can take, and it's impossible for us to go through each one to see which combination produces the best accuracy. So what we would do here is that we would use something such as grid search, that basically automatically goes through each of the different combination of parameters to see which one produces the best results. So if I take an example using XGBoost, for example, in XGBoost, there are many hyperparameters that you could choose from, but I'm just going to look through these, well, 3 actually. I'm not going to be looking through a booster. But let's say we're going through eta, max depth, and estimators. If we were to actually use grid search, what we would do is we would set a parameter dictionary like so, where we would define the different combinations we want the grid search to go through. We would call grid search and then fit using our training data, and basically this would just automatically go through each combination. And then if we call best params, it will produce and show the combination that produced the best results. And so here it ended up being these numbers and these values. And so we would then create our XGBoost model using these params. Okay. And then next is model compression. So there are many reasons why you may want to compress your model. So if I were to give one example, for example, today, many real-world applications demand real-time on-device processing capabilities, meaning that the AI technology must work on edge devices. However, the models that are big in size are typically expected to perform well, but evidently, the bigger the model, the more storage space it will need. On the other hand, edge devices are resource-constrained and have limited memory and limited processing capabilities. So in this case, you might want to opt to have a smaller model, and thus becomes a trade-off between accuracy and size. However, there are also other reasons you might want to compress your model. For example, you might want to compress your model to have higher inference speed. And so in this case, it becomes a trade-off between speed and accuracy. So as you can tell, as a result, model compression is recently becoming a fairly important topic. So these are just some of the various techniques that you can use to compress your model. Today, I'm just going to be explaining pruning and quantization. So if we first go through pruning. So pruning is the process of removing excessive weights, neurons, and layers in a neural network to increase inference speed and decrease model storage size. It can also be used in decision trees. So as you already know, decision trees can be fairly susceptible to overfitting, but pruning this may help reduce overfitting. So there are several pruning techniques that you can use. The most popular and common one being weight pruning. So this is just when you prune weights that are below a certain threshold that you've chosen. You can also do neuron pruning, which, as the name shows, prunes the neurons instead of the weights. You can also do filter pruning. So in filter pruning, what you do is you rank the importance of the filters using the L1 and L2 norm, and then you cut out basically the lowest ranking filters. And then you finally have layer pruning. So these are just some of the techniques that you can use. So next, if I briefly go over quantization. So quantization is a process of converting data that is in floating point 32 bits to something with a smaller precision, such as integer 8 bits, whilst maintaining as much as the original accuracy of the model. By doing this, the size of the model can be greatly reduced. So just to explain this a little bit more, basically, as you can see, the weights here before it's been quantized is like so, and once you quantize it, it becomes like so, which will, again, greatly reduce the size of your model. In both quantization and pruning, there are many different kinds of techniques and many ways that you can implement it into your original model. For example, there is something called post-training compression, where you compress your model right after already building and training it, or you can do compression aware training, which basically means that you can build your models whilst knowing that you'll compress it later. So for example, with quantization, you can quantize the entire model right after building the model, or you can build the model whilst quantizing at the same time. So the latter obviously retains higher accuracy. So while it's not one of, while we don't see it often, there are some previous problem statements that you can look at that used quantization or model compression overall. I'm just going to bring up a few here. The first one being lightning fast modulation classification with hardware efficient neural networks, which is a problem statement from 2021. So in this challenge, the participants will design neural networks with an awareness of both inference computation cost and accuracy to explore the landscape of compact models for RF modulation classification. And the goal here was to use quantization, sparsity, and other training techniques to design a neural network that achieved a minimum accuracy. And these are also some other problem statements that had to do with model compression. So as usual, let's move on now to the Jupyter notebook session. We are actually using the original data set that we used a few weeks ago. So if you could access the GitHub, I'm going to share my screen to explain how this goes. Now, just give me a few seconds. If you have not downloaded the Jupyter notebook from the GitHub, I recommend that you do that now. Today's one is called ML compression. There are two notebooks. There is one with _PR that stands for practice. So that just has the first half of the model building section in it. And then we'll start off from there. That's one that I'll be using today. You can also download the full version, which shows the entire code that we'll be showing today. So this is the code for today. So as you can tell, again, on the GitHub, you can find today's notebooks. There should be two. Oh, well, as of now, there's only one, which is odd. I will actually update right now the second one. This one is the full version. The one that you can find right now here is the short version that only has up to model building and training. I will do that right now. So again, if you have not downloaded this yet, please download it now to follow along with the hands-on session. The data, it can be found in the data file here. You can find it here and here. We're going to be using these two, diff dataset and diff tested. So I will leave everyone a minute to download it if you would like to follow with the coding session. Okay, so if you refresh your tab, they should both be there now. Yes, so this one again is the full version. So if you'd like to just read along, that's also something that you can choose. Okay, hopefully that gave everyone enough time. So the data set we're using today, we used actually a couple of weeks ago. This is from the KDDI data set from the 2021 challenge. So again, here, this is just downloading some of our libraries. We will be downloading more, but these are the ones that we'll be downloading in the beginning. And then you can just load all the libraries here, which is basically just going to download the data and convert it into a data frame that we can see and then scale it here as well. Today, we're just going to be using a neural network here. So I'm just using a sequential model with just dense layers. So dense layers are layers that are deeply connected with its preceding layer, meaning that the neurons of that layer are all connected to every neuron of the previous layer. Here are just the outputs that you can define here and the activation function. You can choose what you'd like. I've just chosen this today. So obviously, if you change these numbers here, you will get different results than what I have. Please make sure to add a final dense layer here that's going to define your output. And then we're going to compile it using an optimizer and a log function. I've also included an early stopping function here, which is basically going to stop the model from fitting if the accuracy doesn't improve. I'm going to train this 200 times, see the accuracy using a test data set, and we'll let it run. So this may take some time. And if you have questions in the meantime, please feel free to put it in the chat. Okay, hopefully that finishes soon. Okay, and as you can see, it stopped early because the accuracy wasn't improving. So if we call history of the model, we can then very easily plot to see what's been going on. And then, as any other model, we'll call the predictions using our okay, and then we'll import mean squared error metric to see how well our model did. And we'll define this as the baseline RMSE, and I'm just going to take the square root of the mean squared error. We'll compare this with our Pruning model later. You can also call model summary if you'd like to see how your model is built. And then we're going to save it as an H5 file. An H5 file is basically a hierarchical data format file, which saves the data in multi-dimensional arrays. And then we're going to save this in a new file that we'll create here called save models. Like so. Okay. Okay, and then we're going to import OS because OS is going to help us get the size of this. And this is just going to give us the size in bytes. Okay, so now let's try and prune the model. I'm going to mark it as pruning. And then here we're going to use TensorFlow today to prune our model. So we're going to import this. And we're going to call this, and we're going to define this function. And then we're going to set our number of epochs. So the number of epochs can be significantly smaller than the original when we first fitted our model. We're going to also declare our batch size. And then we're also going to just declare a begin our end step. Okay. And then this is the important part. We basically have to declare our pruning parameters. For this one, I'm actually just going to copy and paste from here. Pruning params. So this one, just to explain it really quickly, you basically declare your initial sparsity, how sparse you want it, and then your final sparsity, and then your begin step and your end step. And then, just very simply, we're going to prune this model using our declared function. On our models, our original model, and then using the parameters that we've just declared. So just really quickly.
Yeah, on cell 21, just
going to, that is falsely written, but just to keep it intact. And then we're going to compile the model. Like so. And I'd just like to mention here that I'm actually pruning the entire model after, so we're doing post-training pruning. There are obviously other ways that you can prune your model. For example, you can take random layers to prune overall, for example. Obviously, once you do that, your accuracy can be retained a lot better. But as for now, just for a simple explanation, we're going to be pruning the entire model. And then just like we did with the original model, we also do, we do have to declare this part as well for it to work. And that I would just recommend that you copy and paste from the original notebook. I will also include it in the chat. The log is just going to log how the pruned model is working, and then we're just going to fit it as we just did. what I'm just going to do is I'm going to go back to our original file and copy and paste from here. And while we're at it, I'm just going to share screen. And do that again. And then we're going to call current model, change this to callbacks, and change the number of epochs to the ones that we've already declared. Okay, and we're going to let that run.
Whilst we are waiting, please fill in this survey.
I'm just going to let everyone answer the survey real quick. And then again, we're just going to call predictions to predict the accuracy of the model. Again, mind spelling mistakes. And then we are going to see the accuracy. And so to do this, I'm again just going to copy the exact same as we did earlier. And rename this as print. Okay, and then we're going to have to save it just to see the size again. But to do that, we actually need to unpack this file. So I'm going to call model for export, and then we're going to call something called so once the model is pruned, this method basically just restores the original model with the new sparsity weights. And so we're going to call it on our pruned model. And then we're going to save it. In the same place as our saved models. We're going to call it pruned model.h5. Maybe that works. And then we are going to first do a quick comparison on the size. So here, let's just put the size. So the pruned model size is like so. The baseline model size is like so. And then let's take a quick look at the size here. The pruned model size, again, it's in bytes. And the baseline model size before it's been pruned is like so. So as you can see, it's been halved nearly in size. We can also compare the accuracy. So this is the root mean squared error of the pruned model, and the baseline model. This was the accuracy. So as you can see, accuracy was a little bit better for the baseline model. So just as I've mentioned in the PowerPoint as well, we did get a smaller size, however, we did lose a little bit of accuracy. We can also check inference time. So we can quote predictions. So this as well, I'm just going to copy and paste from here as it is a little long to write from scratch. And I will also put it in the chat for anyone who wants to copy and paste it. Basically, we're just going to call the time function, and then we're going to do the predictions for about 100 times. So if you call it just once, it's a bit difficult to tell. So we're just going to call it 100 times to compare the prediction time for both the original model and the pruned model. And if we run that, we'll see sort of the difference in time. I'll just run that real quick. So again, now we have our the prediction time for the pruned model, and then the baseline prediction time. So as you can tell, the overall, if we repeat this 100 times, the pruned model takes less time to predict. So we have better inference speed. So that is pruning. Next, let's try and do quantization. So again, we're just going to be quantizing the whole model after it's already been trained and built. So for this one, we're going to use again TensorFlow. So with TensorFlow, we actually have to create a TF Lite model version of the original model, which is actually a smaller size of the model as well. This one as well, I'm just going to get from here as it is a little long. So again, this just creates the TensorFlow, like the TF Lite version of the model. So this isn't actually quantization. I will again copy and paste this in the chat. And then from here, oh no, sorry. So here, basically, it's converting the model into a TF Lite, and then by adding these two lines here, it's quantizing it. So we can't actually, using TensorFlow, we can't quantize the original model on its own. So we first have to convert it to a TF Lite, and then we basically add these two lines here that's going to quantize the entire model. And now we can save it as a pruned and quantized model. I just want to show that we are using model for export here, meaning that we're not using the original model, we are using the pruned model. So what we're actually doing here is we've pruned it and now we're quantizing it. So now let's get the size. I'm going to go up again just to, this code. So here it's going to be pruned and then quantized. Model size. And here we've saved it as so. So now let's compare the size of all of it. So for the baseline, it was that big, and then for the pruned model, it was this big, and then finally for the pruned and quantized version, it was this size. So again, as you can see, it's gone a lot smaller as we wanted to. So with the TF Lite model, we can't exactly call it, we can't actually call predict as we did before. We actually kind of have to unzip it in a sense. So to unzip it, I'm not really going to explain this code, but you can use this to basically get your predictions for the TF Lite model. So what I'm going to do is, again, I'm going to input this in the chat, you can see. And this will help us make predictions so that we can at least compare our accuracy. So here again, this is also just the second part to get our predictions. Oh, sorry, I've included mean sorry, we haven't used that now. So we get our accuracy of so. So again, if we compare everything, our baseline root mean squared error was so. Our pruned model was so. And finally, our quantized model was so. So as you can see, this time around, the pruned quantized model does decrease in accuracy just a little bit, but not so much different today. Please be reminded that we are using a very simple model. So if you create something a little bit more complicated, you should see a little bit more of a difference here as well. In the original code, as you can see here, the accuracy does decrease just ever so slightly as well. And so there you have it. It's very difficult to predict using the time as we did here, just to see how inference speed is. So I'm not going to do that today, but hopefully this is showing you how quantizing and pruning your model can change in accuracy, but also decrease the size, and that this is something that you can do if you're ever hoping to deploy your model on, for example, edge devices. So that is it from my side. We'll now go into a quick Q&A session for anyone who has any questions.
Thank you so much, Miya, for introducing and for explaining about pruning and quantization, as well as the GitHub repo. Just to add on what Miya has explained, in this practice session, especially, we have used TensorFlow. But of course, there are more, I would say, robust or flexible implementations using PyTorch. As Miya mentioned in one of the slides, that we had a challenge last year. And in that, Xilinx team was requesting participants to create, to increase the inference speed of the machine learning model. So in terms of the deployment, when you're deploying it on an FPGA. And in that implementations, participants were given Brevitas. So Brevitas is a platform, a PyTorch-based quantization platform, and participants it was quite flexible, where participants, they were able to do in-training quantization as well as post-training quantization. So depending on your applications, there are some tools I believe that you can use to compress, for example, to prune or to quantize machine learning model, but depends on which platform you're using. If you're using TensorFlow or you're using PyTorch-based platforms. So yes, and of course we are open for Q&A. If you have questions, comments, please, you can open your microphone and let's have some interaction. Or you can either use the chat. You can put your questions in the chat. We can either, you can say loud your questions, or you can put them in the chat. It's nice to interact with everyone during these kind of sessions. Any comments from you, Vishnu?
I believe not. Yeah, I think it would be good to look at other framework experiments. So yeah, so if somebody is interested, then we can talk later offline.
Yes. Yeah, of course, there is a lot of other frameworks implementations, and if maybe you have an experience working with some kind of framework, or you have some kind of experience, you can also share with us, with others. This is intended to just share the knowledge in a simple manner, in a simple way, where even a beginner can consume and can try out some things, some simple implementations, especially in this journey of machine learning. So we are still open for questions or comments. Anyone with some comments with questions? Okay, seems there's no questions or comments. So at this point, I would like to close the session. Thank you everyone who made time to join our session. We appreciate so much, and hopefully we'll have some more sessions in future. For those that are working on the challenge, please make sure to submit your solutions, and we'll be looking forward to having you in more of our sessions. Thank you so much and have a good day. Bye, everyone.